The point is that science is not decided by authority, it's decided by
The
evidence.
wave of James Webb data has shattered what scientists thought they knew about 3i/Atlas. The third interstellar object ever detected in our solar system was supposed to be just another icy visitor, but the signals released today, pulsing light, a glowing green halo, and fragments tracking in formation, point to something much worse. The strange, repeating rhythms aren't random, they're precise, as if cycled by purpose. And behind every new frame, the data suggests that what's out there doesn't behave like any comet we've ever seen. Is this a natural phenomenon, or the footprint of something engineered? The answers lie in the anomalies that have left experts stunned, and what comes next may force us to rethink our entire place in the cosmos. On July 1st, 2025, the Atlas Survey Telescope in Rio Hurtado, Chile, recorded a faint, fast-moving object against the background stars. The automated system flagged its trajectory as unusual, hyperbolic, with an eccentricity just above 1, meaning it wasn't bound to the Sun or any planet. Within hours, the Minor Planet Center broadcast a preliminary designation, 3i/Atlas, the third confirmed interstellar object ever tracked entering our solar system. Pre-discovery images surfaced almost immediately, with teams at Caltech's Zwicky Transient Facility and observatories across the globe combing through archival data. They found traces of the object as far back as June 14, 2025, each detection tightening the arc of its approach and confirming its origin beyond the solar system. The discovery itself followed a now familiar pattern. A sky survey scans for asteroids and comets, algorithms sift through thousands of moving dots, and, on rare occasions, a candidate appears that doesn't fit any known orbital family. 3i/Atlas was moving too fast, on a path that could only have begun in the darkness between the stars. Initial calculations showed it would pass within 1.4 astronomical units of the Sun, just inside Mars's orbit, before slingshotting back out into interstellar space. Early analysis ruled out any danger to Earth, but the object's speed and inbound angle demanded attention. NASA's confirmation was swift, and soon observatories worldwide began directing their telescopes toward the inbound traveler. For the Atlas team, the find was both a triumph and a puzzle. The last two interstellar visitors, Oumuamua in 2017 and Borisov in 2019, had each rewritten the rules in their own way. Now, with 3i/Atlas, the initial data suggested another outlier, but nothing yet pointed to the extraordinary. The designation was logged, the trajectory mapped, and the world's most powerful instruments, James Webb included, were cued for a closer look. No one could have predicted how quickly routine would give way to unease. Within days of the first Webb observations, a pattern began to surface in the flood of incoming data, a pattern that shouldn't have existed. Dr. Lina Ortiz, a photometry specialist on the James Webb Space Telescope team, flagged the anomaly during a routine analysis of near-infrared camera and mid-infrared instrument time series exposures. Every 2.4 hours, the brightness of 3i/Atlas ticked upward and then faded, repeating with a precision that left less than one chance in 1,000 it was random. Ortiz's team ran the numbers again, this time stripping out cosmic ray hits, dithers, and detector resets. The pulse survived every artifact check, appearing in raw ramps, calibrated exposures, and even in archival Atlas survey light curves. The pulse wasn't tied to the object's spin or to any known resonance. It didn't match the thermal cycles of the telescope or the orbital period of Webb itself. Across filters and wavelengths, the rhythm cut through the noise, a heartbeat, steady and mechanical, as if something inside was cycling power. Ortiz described it in her notes as a metronome against chaos, too regular for a comet, too slow for a satellite, too persistent for a glitch. Colleagues at Gemini and the Zwicky Transient Facility tried to reproduce the signal from the ground. Their data, though noisier, hinted at the same interval, a faint echo of the Webb pulse. By the end of August, the team had ruled out every natural cause they could imagine, outgassing jets, rotational modulation, even solar wind interactions. The periodicity remained. For veteran comet scientists, it was as if a new rulebook had been dropped onto the table. Ortiz's findings spread quietly through internal channels, fueling late-night debates and urgent Slack threads. Each new pulse, each unbroken cycle sharpened the question, Was this the signature of a living process, or the residue of machinery drifting between stars? The first Webb spectra arrived just after midnight. What should have been a faint, diffuse haze around 3I/Atlas instead exploded into focus, a green sphere swelling outward at nearly 5,000 kilometers per hour. The halo's edge advanced so quickly that NASA's own modelers had to check their code for errors. Standard cometary physics predicts a slow, steady release of gas and dust driven by sunlight. But this glow was different. It didn't fade as it expanded, it intensified, as if powered from within. The lab team at NASA's Goddard Space Flight Center pored over the NIRSpec data, zeroing in on a sharp peak at 516.5 nanometers. That's the Swan band, the spectral fingerprint of diatomic carbon, C2, a molecule known for painting comets green as sunlight breaks apart organic ices. Yet in this case, the intensity and speed of the emission shattered expectations. The green shell ballooned to 60,000 kilometers in less than a week, dwarfing the nucleus and outpacing every known comet by a factor of 5. Attempts to fit the observations with standard outgassing models failed. The numbers only worked if the surface temperature of 3I/Atlas was hundreds of degrees higher than physics allows. Some theorized a sudden chemical reaction, others blamed an undetected solar event. But no solar flare, no spike in the wind, no plausible mechanism could explain the data. The coma's expansion was too fast, too uniform, too bright. One researcher described it as an energy field, something closer to a shell of plasma than a cloud of gas. The green glow didn't just defy explanation, it challenged the very idea of what a comet could be. As the halo grew, so did the sense of unease. The team's private Slack channels filled with speculation. Was the emission being pumped by an internal engine? Could superheated plasma account for the kinetic energy? No consensus formed. With each new exposure, the anomaly grew sharper, the boundaries more defined. The mystery deepened, not just a pulse in time, but a transformation in space. The next data drop would reveal if the surface itself held the answer. Polarization data from Webb arrived in September, and with it, a new kind of puzzle. Instead of the rough, chaotic scattering expected from a cometary surface, the data revealed something else: broad swathes of high reflectivity, some areas bouncing back more than 80% of incoming light. These regions didn't just glint at random, they dimmed and brightened in perfect lockstep, as if vast, flat panels were rotating in unison around the nucleus. The pattern repeated with a precision that defied natural explanation. No known mineral or ice could produce such synchronized, mirror-like flashes on this scale. At Harvard's Center for Astrophysics, Dr. Suri Rajan's team ran simulations, mapping the polarization curves against every plausible arrangement of surface frost, dust, and fractured ice. None matched. The only models that fit required broad, planar surfaces, geometry more akin to engineered material than fractured stone. Meanwhile, a different anomaly surfaced from the Pan-STARRS telescope in Hawaii. Amateur astronomers, tuning into a live stream, watched as a string of faint points trailed behind the main body of 3I/Atlas. At first, these dots looked like ordinary debris, but as days passed, their motion told a different story. Each fragment maintained a stable orbit, never drifting, never colliding, their paths so regular that orbital mechanics software flagged the configuration as non-random. In the livestream chat, users began to map their positions frame by frame, noting that the spacing and velocity stayed constant, even as the main object tumbled through space. By mid-September, the grassroots community had logged over 100 hours of continuous tracking. Their data, when cross-checked with Webb's, showed the fragments weren't just tagging along. They were moving in precise formation, echoing the main object's every maneuver. The implication was clear. These weren't loose shards, but controlled companions, orbiting in a way no natural debris cloud could sustain. For the first time, the conversation shifted from chemical oddities to physical intent. The evidence pointed not just to an object built for survival, but to one built for purpose. The question of navigation, how such a structure could steer through the solar system, loomed larger with every new observation. Infrared detectors aboard the James Webb Space Telescope began flagging something no one expected. As 3I/Atlas drew closer to the Sun, a series of short-lived colossal energy bursts lit up the mid-infrared spectrum. Each spike registered at nearly 1 × 10 to the power of 17 watts, an output on par with the total power consumption of human civilization, but unleashed in minutes. The data arrived in encrypted packets, routed through NASA's Goddard Control Center, then quietly escalated to a classified channel. Only a handful of instrument specialists had access to the full flux readouts. One of them, a veteran spectroscopist, described the pattern in a memo later leaked to a defense analyst. No known comet, asteroid, or natural process can generate this kind of power so quickly and then drop back to baseline. The surges didn't match solar flares, cosmic ray hits, or any known background event. Instead, they tracked with the object's approach vector, growing in both frequency and intensity as 3I/Atlas swept inward. More disturbing was the spectral fingerprint embedded in each burst. Alongside the expected glow of heated dust and volatile ices, the Webb team detected narrow, unidentified emission lines, bands that didn't correspond to any known molecule or atomic transition catalogued in comet science. In private Slack channels, NASA's mid-infrared group debated whether these lines hinted at exotic chemistry or something engineered to radiate energy at specific wavelengths. Word spread beyond the science teams. A Department of Defense insider, briefed by NASA's liaison, flagged the event in a secure Space Force digest. The report called out the uncanny regularity and power scale of the surges, likening the signal to the thermal signature of a controlled reactor, something designed to convert energy, not just release it. The memo stopped short of conclusions, but its language was clear. If this is natural, it's unprecedented. If not, we're looking at a technology beyond any known propulsion or energy system. Webb's instruments, built to peer back to the dawn of time, had captured an object just kilometers across, flaring with industrial-scale power in the darkness. The implications rippled through the highest levels of NASA and defense, igniting debates about disclosure, risk, and the boundaries of science. The question now wasn't just what 3I/Atlas was made of, but what it was doing, and why its energy footprint looked less like a comet and more like a machine ramping up for something yet unseen. Webb's color imaging, running across visible and near-infrared bands, began to pick up something even stranger as September waned. Amid the surges and the swelling halo, analysts noticed abrupt flashes, moments when the green envelope snapped to red, then faded back, in perfect sync with the object's heartbeat. The wavelength shift wasn't subtle. Every 2.4 hours, right at the crest of the brightness pulse, the emission at 557.7 nanometers spiked, painting the coma in a blood-red hue for minutes at a time. Then, as quickly as it arrived, the red vanished, replaced by the familiar, unyielding green. No comet on record has ever cycled its colors with this kind of precision. Standard photochemistry can't flip emission states on a timer. Solar-driven comae brighten or fade, but they do not shift hues in lockstep with internal pulses. The pattern repeated across exposures from NIRCam, MIRI, and even ground-based spectrographs patched into the global campaign. Each time the light curve peaked, the color mode snapped, green for the trough, red for the crest. The effect was so regular that data analysts at the European Southern Observatory ran autocorrelation checks to rule out software glitches. The signal held. No instrument artifact, no calibration step, no cosmic ray interference could account for the phenomenon. Debate flared in private Slack channels and late-night Zoom calls. Some suggested a cycling energy system, switching modes for stealth and then for transmission. Others posited a surface layer capable of rapid phase transitions, engineered to emit at different wavelengths depending on internal state. No one could point to a natural process that would explain the timing or the purpose. The color shift tracked the heartbeat, not the sunlight, not the changing distance from the sun. It was as if the object was toggling through operational modes, each with its own spectral fingerprint. The question now wasn't just what powered the glow, but who, or what, was controlling the switch. On October the 3rd, 3I/Atlas swept past Mars at a distance of 28 million kilometers. 4 weeks later, it grazed the Sun at blistering speeds, then threaded past Venus, skimming inside Earth's orbit. These weren't random encounters. Each flyby traced a narrow corridor, so precise that even NASA's navigation teams paused. Monte Carlo simulations, millions of randomized trajectory tests, found that only 0.005% of possible paths matched the one 3I/Atlas actually took. For reference, that's like tossing a dart at a spinning globe and hitting 3 tiny targets on 3 different continents, with the globe shifting between throws. Harvard's Avi Loeb, no stranger to controversy, called the path cosmic choreography. To him, the odds were not just unlikely, they were deliberate. The numbers left little room for accident. If this was a mission, the route was chosen with intent. The question now, what destination could demand such precision? Deep inside SETI's Mountain View facility, analysts began combing through radiologs timed to each Webb anomaly. The usual static filled the channels: solar hiss, cosmic background, the faint whispers of distant pulsars. But layered beneath, at intervals of precisely 4.2 hours, a subtle fluctuation crept into the data. It was not a signal in any conventional sense. No carrier, no modulation, just a barely there rise in noise power, repeating with the patience of a clock. SETI's own autocorrelation routines flagged the anomaly as statistically significant, too regular to dismiss as interference, too faint to decode. Internal memos circulated, marked confidential, debating whether to escalate. Some staff called it a ghost in the data, a side effect of the object's passage through the solar wind. Others, more cautious, compared the pattern to known beacon protocols, sub-threshold pings designed to evade detection. The debate stayed behind closed doors, but the question lingered. If 3I/Atlas was transmitting, who was meant to hear it, and why keep the message so quiet? As October 2025 draws closer, the world holds its breath. NASA's official line remains measured, an unusual comet with properties we've not previously observed. The language is careful, almost clinical, but the data keeps pouring in, and the anomalies refuse to fade. In televised interviews, Neil deGrasse Tyson urges patience and rigor, warning against the leap to alien technology. He calls for more data, more tests, more skepticism. But across the news cycle, the tone is anything but cautious. Michio Kaku, animated and unfiltered, points to the synchronized fragments and the energy surges. To him, the evidence hints at something engineered, a probe or even a mothership. Social media explodes. #Atlas. Alien trends in 30 countries, racking up over 40 million posts in a single week. Amateur astronomers livestream every new Webb update, while talk shows volley between panic and awe. The debate fractures along lines of belief and doubt. NASA's statements grow more guarded. The public's imagination runs wild. With perihelion just weeks away, every pulse, every unexplained glow, feels like a countdown to an event no one can name, and no one can stop. On July 1st, 2025, 3I/Atlas became only the 3rd interstellar object ever tracked entering our solar system. Webb data confirmed a hyperbolic trajectory, 2.4-hour rhythmic pulses, and a green halo expanding at 5,000 kilometers per hour, none of which matched known comet behavior. Polarization maps revealed reflective panels and orbiting fragments, while energy surges reached 1 × 10 to the power of 17 watts, far beyond natural explanations. Despite these findings, NASA statements still call 3I/Atlas an unusual comet, and official radio searches report no confirmed signal, only faint anomalies. The true origin and purpose of 3I/Atlas remain unresolved, with classified details and ongoing investigation. As perihelion approaches in October 2025, all evidence points to an object following a path so precise that chance is less than 0.005%. For now, 3I/Atlas stands as the most anomalous visitor ever recorded, forcing science to confront data that defies every known category. Atlas has changed the discussion about what may travel between the stars.